always. Does the camera work? It does. Okay. We're good. Nice to see you guys. We'll get started with another lecture for the day. Let's see. So, in terms of course announcements, I think your main responsibilities are homework. You also have a midterm coming up, so start thinking about that. Oh, bananas, we forgot to post that stupid quiz again. In future versions of this class, I'm not going to include that. I'm committed to it now because it's on the syllabus, and I know the MIT rules, but apparently we're not responsible enough to write these on time. So at the end of lecture, what I would ask of you guys is to please remind me to write a very easy quiz. Okay, and my apologies, really, teaching a new class, you always end up dropping some random ball or another. Oops, sorry. Ugh. Okay, right, so, and in terms of the homework, at least Axel, I know, successfully completed it in my office the other day, so the rest of you are officially behind. No, but really, do, you know, get help early and often. I know Chris canceled his office hours today because he's out of town. If you need help, maybe I can hang out for an hour after class. It's perfectly fine. You can come to my office. Any questions, comments, concerns on that front? Cool. All right, folks. Well, in that case, we finally come to a very exciting moment that every numerical analysis student must eventually come across, which is essentially to justify what is, like, I think the world's most elegant and beautiful and super nice algorithm in this entire discipline, and also completely obtuse why it should work, which is this QR iteration method that we briefly motivated last time. And there's so many different ways to think about QR iteration. And naturally in the book and in our lecture today, since I couldn't decide on the right story, we're just going to tell like 3 different ones. But the idea here is that essentially, I don't actually know the history of this algorithm. If somebody just like did this by accident and noticed that this algorithm converged, or if there was some intelligent design here. But the basic point is that what we do is we start with some matrix. And today, by the way, we're going to make some simplifying assumptions, which are often true in real life anyway. We're going to assume that A is symmetric with no repeated eigenvalues. I believe both of these can be relaxed, but I'd have to think about it. We can return at the end of lecture and see if that's true. But in any event, that's going to allow us to really easily justify some convergence stuff that otherwise would be a little more technical. Okay? And our goal is to find all of the eigenvalues of A. So far, the algorithms we've talked about have kind of targeted one at a time, right? So we started by just doing eigenvalue iteration, like just basically taking an arbitrary vector and multiplying it a bunch of times. Remember that led us to the dominant eigenvector of a matrix. And in the previous lecture, we saw like a lot of variations on that theme where like, I want the eigenvector with the smallest eigenvalue or the one closest to some constant or whatever. And each one of those things was just some variation of that iterative scheme. And then at the very end of our previous lecture, we talked about these strategies called deflation, which is one way to get more than one eigenvalue, right? Where the idea was I compute one, then I kind of fix it, I deflate my matrix, and then I keep going, right? But obviously that strategy is probably okay for computing a few, but it's not so great for computing a big clump of eigenvalues at a time. Okay, so now we're going to do the opposite extreme. We want the full eigenvector decomposition of A. And here's how we're going to do it. We're going to take our matrix A, and we're going to factor it. So in particular, maybe I factor, this looks tautological, but whatever. So I'm going to factor my matrix A as the product Q times R, just like we've already done a few lectures ago. And now I'm going to take A, and I'm going to replace it with RQ. And that's it. Then we go back to step 1. We just iterate this procedure a bunch of times. And what we're going to justify today is that what we can actually expect is that R is going to converge to a diagonal matrix of the eigenvalues of A up to sign. This is just beautiful. Yes, Axel. Right, so our input is a matrix A, and then our algorithm here is to compute the QR of A, and then replace A with RQ, and just keep iterating. What was that? Oh yeah, otherwise you end up back at A. I think we can all agree on that. Okay, yeah. So flipping the order is pretty critical here. And so this is like the world's most beautiful technique. For those of you who aren't paying attention in class, I encourage you to open up Python and like give it a try. Like generate your favorite symmetric matrix and just run this, and you'll see. Conversion rate isn't awesome, but it does eventually converge. Okay, so this algorithm is mysterious. I mean, like, you know, I think actually a lot of numerical methods books kind of justify it as like, here's a thing we could try. But I do think it actually, there is a reasonable set of logic that could lead you to this technique, and for all I know, maybe is how people got there to begin with. Although my suspicion is that somebody just tried this. Incidentally, I tried on my laptop doing LU factorization and then multiplying UL a bunch of times, and fun fact, nothing interesting happened. Okay, but in any event, this is our basic algorithm, and now our job in the first half of lecture today is to justify it. Okay? In the second half of lecture, we're going to move on to a new factorization called SVD, and my goal here is to at least define it because you need that for your homework. Okay. Everybody on board so far? Fantastic. Whew. So this is our algorithm. It's totally beautiful. It's so nice. It is stunningly elegant. Now let's think about why. So in general, remember that we have this operation where if I have a matrix A and I map it to like T inverse A T, like that, right, where T is an invertible square matrix, then what do we know about the relationship between the eigenvalues of A and the eigenvalues of this thing? They're actually the same. And so, like for example, let's see if I want to do this, or if I'm going to ball up this proof if I do it without it in my notes. So let's say that I take an eigenvector of this guy, for example. So I have T inverse A T x is equal to lambda x, like that. What do you think I'm going to, yes, okay, this is going to work. Fantastic. If I multiply both sides by T, I get A Tx is equal to lambda Tx, like that. So obviously, if I kind of group it like this, what I've justified is that Tx is an eigenvector of A, right? Moreover, you have to double check that Tx is non-zero, but that kind of follows from invertibility. Okay? So, and then I'll let you think about the reverse direction. So this is called a similarity transformation. And remember like the kind of the name of the game in a lot of the algorithms we've cooked up in this class, like QR and LU and so on, is to like come up with some operation that I can do on a matrix that modifies it but brings me closer to my goal. Right? So for example, for LU, I was pre-multiplying by elimination matrices. For QR, I was pre-multiplying by householder or post-multiplying by elimination matrices and so on. So now we have kind of a hint as to how eigenvector algorithms work. They start with a general matrix A, and now they apply these similarity transformations until they eventually converge to something really simple. And of course, in an ideal universe, I mean, what's the simplest possible thing? It's a diagonal matrix, because what are the eigenvalues of the diagonal matrix? It's just the values along the diagonal, yeah? So then the question is what T to choose. And of course, in the interest of designing an efficient algorithm, I think a relatively reasonable question you might ask is like, okay, well, I might as well work in a class of T's that's easy to invert. Right? And the easiest class of T's to invert would be orthogonal ones, right? Because in that case, Q inverse is equal to Q transpose, and it's a heck of a lot easier to multiply by the transpose of a matrix than by its inverse. These are just like design desiderato. Like if you were trying to, like, you're the first guy to come up with these methods, and you're trying to kind of think of the logic that like might have led somebody to one of these, this is my best guess. Okay? So I have a matrix A. I'd like to apply some similarity transformations to it, and eventually find some nice structure. The only question is, well, what Q makes sense? And so far in this class, we've only encountered one Q, yeah, and that's from the QR decomposition itself, right? And notice the following: that if I take A and I conjugate it by Q, so I do like that. Well, remember that A is equal to QR, so I have Q transpose QR Q, like that. Right? This thing is the identity matrix, and our Q is what's left. So notice that the QR algorithm can be understood as repeatedly conjugating by Q. These are the same thing. But this is starting to become a little less mysterious. So at the very least, what we've shown is that successive iterates of this method have the same eigenvalues. We haven't justified convergence, but at least we know we haven't screwed anything up. That make sense? Any questions so far? So there's a lot of different ways to think about what's going on in this method, we're going to justify many different versions of this. And we'll see that at the end of the day, I think we can all kind of decide that this is actually kind of a reasonable method. Right, so here's our little story so far. Right, so here's our algorithm. Couldn't be simpler. I'm going to introduce a tiny amount of notation, which is that qk and rk are the QR iteration of the kth, the QR factorization of the kth iteration of this algorithm. And then ak plus 1 is the rq product. So in other words, like just for math, it's going to be useful for us to keep track of what iteration we're in. Okay. So in order to justify this algorithm, we're going to use one more fun fact from linear algebra. This is one you may or may not have seen in the past, but it's not so hard to prove, so we can just do it. And that is the following. Suppose that I have two matrices that have a full set of eigenvectors and distinct eigenvalues. Now you can see why we asked that for A. Then those matrices commute. In other words, A times B is equal to B times A, precisely when they have the same eigenvectors. They may not have the same eigenvalues, but they have the same eigenvectors. This is the fact we're going to use to justify our technique. Any questions about the statement of this little proposition? This actually shows up in a lot of places. It also shows up in PDE every once in a while in kind of disguised form. Okay. Well, so let's prove this thing. The class across the hallway sounds way more interesting than this one. I'm so sorry. Okay, so let's go the forward direction first. So let's say that we have, I guess the reverse direction, the way I stated it here, the forward direction in my notes. So suppose that they have the same eigenvectors. Let's show that they commute. Okay. So suppose A and B have eigenvectors. We'll call them x1 to xn. These are in Rn, like that. But remember, they may have different eigenvalues, so we're going to have to distinguish, right? So in particular, values lambda 1 through lambda n, A, and lambda 1, B through lambda n, B. Right? So what we want to show is that they commute, right? Okay, so one way to show that two matrices are the same is to show that their product with any vector gives you the same result, right? A matrix kind of is as a matrix does, in some sense. So in particular, take y in Rn. Now, because our full set of our eigenvectors is blah. I'm struggling with sentences today. Because our set of eigenvectors spans Rn, we know that we can write y in that basis, right? So in other words, we can write y is equal to the sum of ai, xi for a suitable choice of a's. Everybody with me so far? Cool. So what do you think we're going to do? We're just going to do the two products and show the same. We don't want to think too hard. Okay? So which one do we want to do first? BA or AB? You wrote AB in your notes. Okay, so let's do BA. That way we'll finish your notes. Okay, so this is BA times the sum of, probably choosing the letter A here was not fabulous, but we're committed now. AI times XI, like that. Okay, clearly I can distribute in the sum, so this is AI, B, A, xi. Okay? But remember, x is an eigenvector of A with eigenvalue lambda A, I. Right? So this is the sum over I of AI B x I times lambda I A. Yeah? Yes, excellent. You mean this guy? Oh, all I did was just, this is a matrix vector multiply, and that's linear, right? So I just distributed it over the sum. The A's are scalars. Yeah. Mm-hmm. Any other questions while we're stuck? Okay, so now we have bxi, but x is also an eigenvector of b, yeah? So this thing at the end of the day is the sum ai lambda I A lambda I B xi. Make sense so far? Okay, so now AB times Y. I think we can all agree that precisely the same set of mathematical steps applies here. equals sum over AI times lambda I A lambda I B xi. Right? These two things are equal to one another. So what have we shown? We've shown for all y that AB times y is equal to BA times y. Right? If we step back 10 feet from this little derivation here, which is it. Right? That's all we have to show. Okay, so we've shown one direction, right? We've shown that if you have the same eigenvectors, not necessarily the same eigenvalues, then your matrices commute. Now we have to do the other thing, right? We have to show if you commute, then you have the same eigenvectors, right? And again, and this is the direction where we're going to need to use the fact that the eigenvalues are distinct. Right? We haven't used that yet. Okay. So now, suppose A, B equals B, A, like that. And now we're going to take an eigenvector, x, so we're going to say ax equals lambda x. Cool? Okay. So here's a kind of sneaky trick. I like this proof. All these proofs in linear algebra are just like clever little small things. So in particular, what is a times bx? Well, if I parenthesize the other way, remember ab equals ba, right? So this is really b times ax. We know that that's lambda x, right? So this is lambda bx. Cool? So let's take a look. What do we justify? Well, we just showed that bx is equal to, is an eigenvector of a. Sneaky, huh? Okay, so we have actually two cases. So one, bx is not equal to 0, right? So if this is the case, then as we said, bx is an eigenvector of a with eigenvalue lambda, right? I mean, that's essentially what we just showed, right? Now here's where we're going to use our assumption, right? Remember that we assume that a has no repeated eigenvalues. So what does that tell us about the relationship between bx and x? Well, they got to be multiples of each other, right? Because essentially, there's only one vector with eigenvalue lambda, right? And that vector, we gave it a name. The name is x. We just showed that bx has the same property. So necessarily, we must have the case that bx is equal to cx for some c. Isn't that clever? So in other words, what did we just show? Well, we showed that x is also an eigenvector of b. Yeah? So there. Okay, so now we need to do the second case, which is bx equal to 0, but this is actually still showing that x is an eigenvector of b, now just with eigenvalue 0, right? So in either case, we said for any eigenvector x of a, we've just shown that x must be an eigenvector of b. Notice, by the way, that there doesn't have to be a relationship between that c and the lambda. Like, they can be different eigenvalues. We've just shown that the eigenvectors are the same. Everybody with me so far? These arguments, I think, are easy, but like also easy to kind of screw up in your head a little bit. Cool. So I claim we're done, right? Because we just showed that all eigenvectors of one of these guys are eigenvectors of the other. The eigenvectors span Rn. So necessarily, that's it, right? We're done. Fantastic. So we've proven this fun fact. If you're a math student, you might ask a question about like what happens when A and B are infinite dimensional, like I'm in a Hilbert space. Can I write down a similar result? And the answer is yes, of course. Okay, so we're going to use this, this fact to justify the QR algorithm in a few different ways. We're going to start with like a bit of an intuitive argument, and then we're going to go back and do one that's a little more careful. Okay? So our intuitive argument is going to do the following. So let's say that I coded up QR iteration just for yucks, and I noticed that it converged. And now I might, as like just a back of the envelope kind of calculation, say like, suppose that it does converge, like what does it converge to, right? That's different than saying why should it converge, right? But at the very least, like if it did converge, then like we might ask like, well, what Q and R would satisfy that? So if you think about it, if I reach a fixed point, then essentially at infinity, I have this funny effect, right? That I've converged to some matrix where QR is equal to RQ, right? Because in every step of my algorithm, I'm essentially doing nothing. Now, do you guys see where the proposition on the previous slide is going to apply? Because now we know that the QR, the Q infinity and R infinity commute. Okay. So, in particular, so we have Q infinity, R infinity equals R infinity, Q infinity. I don't love this notation because the word infinity has a lot of syllables, and but we're committed now. Okay, and in particular, remember a different property, which was actually what we started with, which is the following: that A infinity is equal to Q infinity transpose A infinity Q infinity, right? Because this was actually how we derived the QR algorithm. So these are our equivalent statements. Okay. From this expression, if I pre-multiply both sides by Q, then what am I going to show? I'm going to show that Q infinity times A infinity is equal to A infinity times Q infinity. Okay? So like, there's just a lot of matrices here that commute. They all have the same eigenvectors. Okay. So, anybody have an idea what we can do here? So what do we think? So like Q is an orthogonal matrix in particular, right? So like what are likely to be the eigenvalues of Q? They're not like necessarily 1, but their magnitude in complex spaces is certainly 1, right? Because like Q is like a rotation. It doesn't change length, right? I'll let you guys justify that fact at home, but essentially what we can kind of claim is that Q infinity has all eigenvalues. Oops. For some reason in my notes I say that they're plus or minus 1, but that's not actually the case. They're 1 up to with magnitude 1, right? Because they could be complex numbers. I should go back in the textbook and double check that I didn't write the other one. Or at least that I have a better justification of it. Okay. So, suppose A infinity times some x is equal to lambda x, like that. Notice I don't really have to write lambda infinity because I showed that every step leaves the eigenvalues alone. Okay. Right, then what do we show? Right, so AX here is equal to Q infinity R infinity x, which is equal to R infinity Q infinity x, like that, right? Ah, okay, yeah. And what is this thing? Well, certainly if R is real valued, which we know that it is because A is a symmetric matrix, right? Well, then this thing had better be equal to plus or minus R infinity, oh, that's an infinity in case you're wondering, x. Do you guys see why? Because we know that the eigenvalues have magnitude 1. We know that x here had better be real valued. So when we put those two things together, we end up with a plus or minus here. Okay, so this is great, because what are the eigenvalues in an upper triangular matrix? It's actually just the values down the diagonal. If you haven't seen that fact before, the way to remember it is remember that one way to get eigenvalues that's like numerically not such a good idea, but like mathematically perfectly fine, is to look at like r minus lambda I, like that, right? And what you'll end up seeing is that this is equal to just literally the product of RII minus, like that. Right? If you look at the determinant formula, that's kind of not surprising that that's what you should get. Cool? All right, so now we're in good shape, right? Because if our QR algorithm converges, then now we can just read off the eigenvalues as the diagonal of R. Yeah? So now we're doing pretty well. And you guys are going to remind me to double check that the book doesn't do that wrong. Okay. Cool. By the way, notice that essentially what we showed is that the eigenvalues of A end up on the diagonal of R up to sign. We can actually remove that up to sign part, just FYI. Remember when we talked about householder reflections and the fact that we like kind of stick a minus in there just so the determinant of the householder matrix is 1 again? So in that case, you can kind of convince yourself that you don't need the plus or minus anymore. But regardless, it's not so hard to check. Okay. So now we're sort of just accumulating evidence why this QR algorithm might be useful, right? So now we've kind of justified that like flipping QR and RQ is basically the same as conjugation, so it leaves eigenvalues alone. And moreover, if it converges, it has this magic property that I can just read off the eigenvalues, which is pretty cool. Okay. So now let's think about some other reasons why this algorithm might be kind of a reasonable thing. In particular, remember that all of our eigenvalue algorithms until this one kind of had the same flavor, which is you take a vector and you just multiply it by itself a bunch of times, right? And it would be interesting if we could somehow relate this strategy, which feels quite different, to that one. And it turns out that you can. Okay, so here's how we're going to do it. So first of all, what was I doing? Oh, right, yeah. So let's say that I take a to the kth power, like this. So let's reverse engineer this a little bit. You notice that our argument, there's like a lot of kind of circular stuff. We keep adding detail. I'm going to write something really profound. This is equal to a to the k minus 1 times a, like that. And now let's do a really weird thing. So this is equal to a to the k minus 1 times the first column of a to the k minus 1 times the second column of a, and so on, to the nth column of a. Right? I haven't done anything like super exciting here, but just like, this is fun fact that like, yeah. Here. Okay, here's the thing. If I take just about any vector and I multiply by a enough times, where do I end up? Well, I converge to the dominant eigenvector of a. And it turns out, even though like I happen to choose my initializer as one of the columns of a, that still is typically the case, except in very rare situations. And so, in fact, here's a kind of fun thing we can do. Let's say that I factor this guy as q times r. Okay? Now, what does QR factorization do? Like, let's remember the Gram-Schmidt algorithm, right? It like takes the first column and it normalizes it, and then it projects it out all the remaining ones, and then it takes the second column and normalizes it, projects it out all the remaining ones. So, what is the first column of Q as k gets really big? It's the dominant eigenvector. That's exactly right. Why is that? Well, it's just a to some big power multiplied by a vector divided by its norm, right? Now remember how like deflation and all those strategies work. If I project that out of everything else, and then I do QR eigenvalue multiplication, what's the second column of Q going to converge to? The second eigenvector, right? And so on, right? Isn't this handy? So in fact, QR iteration is so magical that not only does it give us the eigenvalues, it gives it to us in order. Yeah? They're sorted from biggest to smallest on the diagonal of R. Yeah? Now, the reality is, this formula here, assuming that you buy that this reaches the eigenvectors of A, which is like not entirely obvious, like because we made a specific choice of things to multiply by here. But if you buy that, here's a really dumb algorithm, which is I'm going to choose a really big K, like, I don't know, 300. That's big. Now I take A, and I multiply it by itself K times, and then I compute the QR factorization once, right? And then this little argument here justifies that, like, yeah, Q will roughly give me the eigenvectors of A. Does that make sense? Let me repeat that. Basically, I compute this thing for a big K, literally I just call my matrix multiply code a bunch of times, and then I do a single QR when that's all done with, and then Q gives me eigenvectors. And this argument shows that like that's basically, you know, like that will give me a reasonable set of eigenvectors, at least in theory. What goes wrong in practice? Do I ever want to take a matrix to a big power? No, that doesn't sound like a good idea. Okay? And moreover, by the way, notice that the columns of a to the k, well, they all converge to multiples of the dominant eigenvector, right? So if I do that, I'm just going to get a bunch of repeats of the same column numerically. Okay. So, but we kind of like this algorithm in theory. Like in principle, that's perfectly fine. The question is if we can do it in a numerically smarter way. And of course, the answer is going to be yes, using QR iteration. So in particular, let's see if we can justify this trick. I think this algorithm is so cool. Like everything about this is just so neat. It all fits together so cleanly. Okay. Hopefully I'm just demonstrating enough enthusiasm. Like this is neat. Like so some of these things are messy. This one's not. This is so cute. Okay. Ugh, chalk. Okay. Only MIT had whiteboards. So here's what we're going to do. We're going to take successive powers of A, and we're going to show that they can be written in terms of the iterates of our algorithm. This is a fun trick. Okay. So in particular, just by definition, our input matrix A is equal to Q1 R1, like that. Cool? This is just like the first step of our algorithm. Okay? So now, let's say I compute A squared, which does not happen in our algorithm, by the way. Well, what is this? Well, we know that we factored A as QR, so we can just write that this is Q1 R1, Q1 R1 again, like that. Hopefully we all agree. How could I simplify this expression? Any ideas? A really pretty thing is about to happen. What was that? That's right. Look what we've got there. We got the next iterate, right? So what is this thing? This is actually equal to Q1, Q2, R2, R1. This is starting to make us conjecture the form for a general A to the K, but let's do one more just for good luck. Okay? So in particular, what is A cubed? Well, of course, it's, which side do I want to do it? A squared times A, like that, right? So we know A squared is Q1, Q2, R2, R1. And then what is A? It's Q1, R1. Sorry for terrible handwriting. Okay. We have R2, R1, Q1, which is the same as Q2, R2. So this is Q1, Q2, R2. Now this thing is Q2, R2, right, times R1. Now what? I know you know. Yeah, Q2, R2 is, well, it's the same as Q3, R3. Or sorry, I said it wrong, but I made the right gesture. R2, Q2 is the same as Q3, R3. In general, by the way, what fact am I using? I'm using the fact that RK, QK is equal to QK plus 1, RK plus 1, right? That's essentially what I'm using here. Okay, so this is equal to Q1, Q2, Q3, R3, R2, R1. Isn't this cool? Okay, so we write a dot, dot, dot. That stands for proof by induction. And we write, at the end of the day, a general form, which is the following. A to the k is equal to Q1, QK, RK, R1. And notice that these QKs and RKs were never explicitly computed by taking big powers of A. They were computed using our algorithm. Make sense? So, what is this object? Well, notice the product of orthogonal matrices is what? It's orthogonal, right? So let's give this thing a name. Let's call it Q. Maybe Q infinity with quotation marks around it because we chose K. Okay? What about the product of upper triangular matrices? It's also upper triangular, right? So let's call this R infinity, where here infinity equals K for some big K. So, what just happened? Well, we can actually get the QR factorization of a to the k as just the product of the q's that we compute during our QR iteration algorithm. Cool? Okay, so now we're getting somewhere. So in other words, essentially what we've shown is that the columns of q1 dot dot qk converge to the eigenvectors of A. Okay. This is cool. Everything about this is so cool. It just all fits together. Okay, so we're gonna do one last thing. Like, so now we have some way of maybe thinking about getting the eigenvectors. We can certainly edit the QR algorithm to just like keep a running product around. That's like perfectly fine. But let's say that we want a clear way to get the eigenvalues. Finally, we can do that. Okay. This is the last little part of our proof, and then we'll talk about SVD. No, we won't. We'll talk about conditioning. Yes? Yeah, we already showed the show up on the diagonal R. We can show that actually it's even cleaner than that. That's just is what will justify next. Okay. And why is that? But what happens if I take a matrix and I conjugate it with this set of eigenvectors, assuming they're orthogonal? Well, then I get a diagonal matrix of the eigenvalues, right? That's what it means to be diagonalizable, right? So here's what we're going to justify. At least when A is symmetric and has no repeated eigenvalues, we're going to justify that actually R is not going to converge just to something upper triangular. It's going to converge to a diagonal matrix of eigenvalues. Okay, so let's do that. Okay. Right, okay, sorry. I have to, thinking is hard. Okay, so, right, so here's how we're going to do it. Now we're going to kind of do the opposite of this argument up here. We're going to instead like write expressions for the AIs in terms of these Q factors. Okay? So in particular, it looks something like this. So the A1, like the first iterator of our algorithm, is just equal to A, clearly. Okay, the A2 is going to be equal to R1 Q1, like that. But remember that like our little conjugation property is that this is Q1 transpose A Q1, kind of by definition, right? Not by definition, because by the fact that we wrote it down earlier. Okay, what's going to be A3? Well, this is equal to R2 Q2, like that. Okay? And of course, again, by our conjugation property, that's the same thing as Q2 transpose A 2 Q2, like that. Okay. Well, now we have an expression for A2 here, so let's plug it in. So this is equal to Q2 transpose Q1 transpose A Q1 Q2. Okay, so we're okay by doing induction at this point. So in particular, we show that A k plus 1 is equal to Q1 to QK transpose A Q1 to QK, like that. Okay? But remember that these guys, this product, converges to the matrix of eigenvectors. Yeah? So what is A going to converge to? Well, A is just that conjugated with the Q's. So now what we've shown is that this goes to a diagonal matrix of the eigenvalues. Cool? All right. So in any event, that I think basically justifies our QR iteration story here. That essentially thanks to these two relationships here, what we've shown is that like doing this QR iteration is very closely linked to just taking a high power of our matrix and then doing a single QR. And moreover, because of that fact, we really can expect this thing to converge to eigenvalues and eigenvectors. Now, what we've written down here is hardly a proof. In particular, I think the only really fishy part of this, I mean, there are a few subtly fishy parts, but the obvious fishy part is this little thing where we, I erased it, right? That we wrote like AK is equal to A times A to the, whatever, like A to the K minus 1 times A, right? So in other words, like we need to justify that with high probability eigenvalue iteration on a column of A converges properly, right? So that's something I'll let you guys think through a little bit. But other than that, our derivation is pretty much okay. All right, so this pretty much concludes our discussion of eigenvalue computation algorithms. But that's not to say that that's the only things out there in the universe. There are so many. This is a thing you could fill an entire course with. For example, just the algorithm that we covered actually is used in practice, but with like a few accoutrements that make it more efficient. So in particular, there's a really clever algorithm out there where you can come up with orthogonal matrices that you pre and post multiply by to make your, I forget if they're orthogonal or invertible. I'm not entirely sure. To make your matrix tridiagonal. This is called tridiagonalization. It's a little bit outside of the scope of this course, but I encourage you to Google it. And the reason to do that is that then your matrix multiplies are much faster, right? Because almost all of your matrix is 0. There's also a whole set of techniques out there called Krylov subspace methods, which like try to uncover some fraction of the eigenvectors, but not the whole set. So like QR iteration can be understood as that to the extreme where you want the full set of eigenvectors. Yeah? Basically, my advice when it comes to eigenvalue computation is my advice for a lot of numerical algorithms, but especially in this domain. Like people build entire careers on clever techniques that are stabilized and smart for computing eigenvalues. Unless you have a truly unique reason why you need to code up your own technique, I would strongly suggest you just call one of the many libraries out there that's pretty well established. But now you know how they work. And they're all like basically built on the same dumb fact, which is that if I take a vector and multiply it a bunch of times by a matrix, I eventually get something parallel to an eigenvector. Okay, so to wrap up our discussion of eigenvectors, there's really one thing left to do, but I think because we're running a little behind, I want to make sure you have what you need for the homework. We're maybe going to omit it, and you can read it in the book. Essentially, the one last thing that really is worth discussing is the conditioning of the eigenvalue problem, right? If we want to continue our usual story, right? We define a numerical problem, we talk about why it's useful, we derive some algorithms for solving it, and then we have to go back and make sure it's well posed and not too sensitive to the input data. Essentially, the proof for this looks an awful lot like the conditioning proof that we already saw for linear problems, right? So we kind of take a small delta, but now we have to take a delta, an x, and a lambda, and an a all at the same time. We make a few approximations, and what we end up with is kind of an interesting problem. I'm rushing through this only because I don't think it matters a whole lot, which is that like the condition number is sort of related to the relationship between the eigenvectors of A and the eigenvectors of A transpose. These are called the left and right eigenvectors of a matrix. And in particular, then, for symmetric matrices, this is a well-conditioned problem, which is kind of unsurprising. So in any event, I'm going to let you guys read about that in the book because we're a little behind. I think it's more important to talk about the SVD unless there's any strong objection. Good. Especially because I don't remember the proof. Good. All right, so with that, we will approach the preview of matrix factorizations, the one that everybody knows and loves, uses every day in their robotics lives, their computer graphics community, their statistics, everything else. This is the one that shows up as the workhorse of numerical linear algebra, and that is called the singular value decomposition. And I'm guessing many of you guys have already used it in your code somewhere, whether or not you understood it or not. Okay? So we're mostly going to talk in this class about applications and uses of the SVD, because what we'll see is that it's computable using an eigenvalue problem. So like it's actually, as like an algorithm question, the techniques for computing SVD are not all that far off from the ones for computing eigenvalues. But we have to make that link first. Okay? So unfortunately, at least when I read a lot of introductions to the SVD, I don't love them because they tend to do this weird thing, which is they say like, suppose I have a matrix. Here's a miraculous property. It can be factored as the following product. And then they kind of go back and prove it. And I've always found that to be a little bit like, I don't know, kind of unsatisfactory, right? Like it doesn't really help me understand why anybody would have thought of this object to begin with. So I'm going to make a lame attempt to justify why somebody might study the SVD and like come across it. Like if we were the first people to wander into the linear algebra universe. SVD, by the way, is a relatively recent contribution relative to what we've done before. Like LU and LU, QR, and eigenvalue decomposition go back to like 1800s, if not earlier. SVD is more of a modern invention because it's more of a computational convenience than anything else. Although I'm sure there exists some manuscript from like the BC times that has like some version of SVD. Like every time you make a claim like that, a math historian likes to tell you you're wrong. Right. So here's one way to understand the SVD. What does a matrix do? let's think about that. So first of all, a matrix, if I think about it, kind of like just defining a linear operator, right? Essentially, one way to motivate the SVD is to think about the following things. So now, by the way, our matrices, unlike the previous lecture, they do not have to be symmetric. They don't even have to be square. In fact, I think it's good to like kind of think of non-square ones to make sure we're not accidentally using properties that we shouldn't. Okay? So in general, right, we can think of the following map, which takes a vector x, which is in R n, and maps it to ax, which is in R m. And it might be useful just to study the geometry of this object. And we all draw the same picture, right? Which is that like you maybe start with, if n and m are equal, you maybe start with a unit circle, and then it like maybe shears and rotates and ends up something like that, right? And I feel like this prototypical diagram has appeared in countless linear algebra textbooks. Okay? And so the SVD is basically just an attempt to decompose this into a stretch and a rotation. That's really all it's doing. And so essentially what we're kind of formalizing is staring us in the face in this picture, which is that there's like a major axis and a minor axis to this ellipse, and that we're kind of stretching in those major and minor directions, and then like rotating the ellipse out of the coordinate plane. Okay? And so that's really what we're aiming for. But if we wanted to dive into it in a little more detail, you could ask, like, well, what are some reasonable ways that we could study the geometry of a matrix? And one of them that was proposed by Rayleigh, probably in God knows when, is to study this particular object. This is called the Rayleigh quotient. R stands for Rayleigh, which is the norm of AV divided by the norm of V. So this takes any vector, and basically it's just measuring how much A stretches it out. Does that make sense? And let's say that, like, just for fun, we were studying the matrix A, and we wanted to know, like, for example, where does this thing reach a local maximum and a local minimum, right? Which from that diagram, we kind of know it's going to be the points of the ellipse, but we don't know that yet. Like, for all of maybe matrices take a circle and map it to, like, a star. Like, like we haven't actually justified that picture so far. Okay? So, if this is our sort of starting point, one thing we could do is compute the critical points of this thing, right? Just optimize, which is sort of what we're programmed to do in this class. Now, first of all, notice, by the way, that R of any alpha times V here is just equal to R of V, right? Because if I scale V up, it comes out of the norm. Yeah, and then you just divide the numerator and denominator by the same thing. Here, by the way, we're going to assume V is non-zero. Okay? So, so it's perfectly fine to constrain our search to the space of V's that have norm 1, right? Because outside of that space, nothing interesting happens. Okay? You can probably see where we're going with this. Right? Then, for example, if I wanted to find the biggest stretch of my matrix, here's the problem I might solve. I might do the following. I might look at V's and maximize the norm of AV, maybe squared just for computational convenience, subject to the constraint V has norm 1. This sounds familiar, right? How many times do we have to do the same proof? So what are the critical points of this problem? Well, what we've shown very extensively in the last couple lectures is that these satisfy this property for some lambda, right? Hopefully we're comfortable with that by now. So, and moreover, by the way, we know that lambda is greater than or equal to 0, right? Because remember, it's the optimal value of this objective. Okay. Everybody with me so far? We don't have to be. Okay. So in particular, the critical points of this thing, right? Like all the points where it reaches max, the local min, a saddle, anything else, they satisfy this relationship. And now that we have the spectral theorem on our hands, right? A transpose A is a symmetric matrix. How many critical points are there for this thing up to sign? Well, there's let's see here. A is m by n, so this thing is n by n, right? So there's n critical points up to sign. So I guess 2n really. And each of them is an eigenvector of this matrix. That make sense? Okay. So essentially, one of the ways that you can understand the SVD is that like you're using critical points of this Rayleigh quotient to kind of study the geometry of a matrix. That make sense? But there's kind of a weird thing that happened, which is that we wanted to understand the map from V to AV, but then when we look for critical points, we ended up not with A, but with like A transpose A. And so I think a reasonable question you might ask is like, what is this dude? Right? Like, what is A times V? Okay. So, I hate this thing. So let's do that. Oh, it's okay to erase the QR iteration? This is old news? Yeah, okay. All right. So, in particular, so let's say that we have A transpose A times VI is equal to lambda I times VI, like that. And now we're going to define a funny object, which is UI star, which we're going to call A times VI. The star here is because we're going to have, like, obviously, for those of you who are familiar with the SVD, eventually we're going to factor as U sigma V transpose. And these are going to be like the columns of U and V, but we're going to have to rescale the U's to make that happen, which is why there's a star for now. Okay, so here's a fun thing. So first of all, we know that A transpose A VI is equal to lambda I VI, but now we've given this thing a name. So in particular, we know A transpose times UI star is equal to lambda I VI. Cool? All right. So now let's do a funny thing, which is let's pre-multiply both sides by A. Okay? So in particular, we have A transpose UI star is equal to lambda I times A VI, like that. But what is A VI? Well, again, that was what we defined to be lambda I UI star. Cool? So what did I just show? So I have AA transpose times UI equal to lambda I times UI. So I started with an eigenvector of A transpose A. I pre-multiplied it by A, and I got something that looks like an eigenvector of AA transpose. Does that make sense? So this is where we're starting to get some intuition. Like there's some relationship between the eigenvectors of A transpose A and AA transpose. They're not the same. They're not even the same space, right? Like one's in Rm and one's in Rn, but they're linked to one another. However, there's one case I have to be the tiniest bit careful about, which is the case where A times V is equal to 0, right? In that case, I have not shown that I have an eigenvector. I've just shown that 0 times something is equal to 0. Okay, so in particular, what I've shown is that UI star is an eigenvector of AA transpose when it's non-zero. Okay. Moreover, let's compute the norm, by the way, just while we're at it. So what is the norm of UI star? Maybe squared. So this is, of course, UI star transpose times UI star, like that, right? And again, we'll just go back to our definition, right? So this is VI transpose A transpose A VI, but conveniently, like this object is an eigenvector, right? So this is lambda I times vi transpose vi, which is just 1, maybe by convention. Cool? Now we're cooking with gas. By the way, if you didn't believe me before, the lambdas are positive. We just showed it by accident, at least non-negative. Okay. Cool. By the way, this is the norm squared, so of course, the norm of ui star is equal to the square root of lambda I, which is what we're going to call the singular values of our matrix in a bit. Okay, so essentially, we've shown 2 cases. One is that, right, so maybe I'll just write it down, sorry. It's getting lazy. One is that lambda I is not equal to 0, in which case we have ui star, which is equal to a vi, is an eigenvector of a transpose with norm ui star is equal to the square root of lambda I, like that. And otherwise, lambda I is equal to 0, and ui star necessarily is also equal to 0, right? Because it's the norm. Everybody with me so far? Okay. So essentially, what we've learned so far is that the non-zero, or really the non-zero or positive eigenvectors, yikes. The positive eigenvalues of A transpose A are somehow very special, right? They map on to eigenvectors of A transpose. Okay? So, so let's take K to be the number of non-zero eigenvectors, or eigenvalues of A transpose A, like that. Okay? Then, essentially, what we have is we have V1 to Vk, which are going to be eigenvectors of A transpose A. These are Rn, like that. And we're going to have corresponding U1 to UK, and I'm going to drop the star. We'll see why in a second, like that, with a bunch of different properties, right? This is what's so cool. So we have A transpose A times VI is equal to lambda I VI, right? We're going to have A transpose times UI is equal to lambda I UI. We're going to define the U's to be the U stars divided by their norms, right? So at the end of the day, we're going to get that A times VI is equal to the square root of lambda I times UI. You see that? Because the square root of lambda I is the norm, so if I've normalized. And similarly, A transpose times UI is equal to the square root lambda I VI. All kinds of relationships here. In fact, we can prove one additional fun fact, which is UI transpose A VJ. Well, what is this thing? This is, for example, A transpose UI VJ, like that. Okay? But by this property here, this is square root of lambda I times VI transpose VJ, which is maybe lambda I delta IJ, where here this is the notation that's like equal to 1 when I and j are the same and 0 otherwise. Everybody with me so far? Okay. Isn't this cool? We're starting to glue these two things together. We now understand the input space and the output space of A. Okay? So now we have to be the tiniest bit careful to go from this form to the SVD because we only computed K eigenvectors and not the full set. We need to make all our dimensions kind of work out. Okay. But that's going to be okay. All we're going to do is fill in the remaining 0 eigenvectors in a careful fashion. So let's do that. So in particular, let's define U bar to be the matrix which is U1 to UK, like that. And similarly, V bar is going to be V1 to VK, like that. Okay? So what have we shown so far? So essentially this property here, right, this delta ij property that we wrote down, we can kind of matrixize it. And when we do, the expression that we're going to get is U bar transpose times A times V bar is equal to a matrix we'll call sigma bar, where essentially this thing has the property that sigma bar is equal to the diagonal matrix of square root lambda 1 to the square root lambda k. Right? So this is just like a slick encoding of this expression up here. This feels like the SVD, right? That's because it almost is. But notice I'd like to factor A, and I didn't quite do that. I have the U's on the wrong side. And sadly for us, because these things aren't square, we have to be careful about what we can invert. So there's sort of two different ways we can go about this. Yeah, let's do the one that's in the book. Okay, so right. What we can do is just complete U to a full U in R M by M, and V in V bar is going to map to a V in R N by N by adding null space vectors. So in other words, like, what do we know about like the remaining set? Like, if I want to span Rn, then I take like the columns of V, and then I just start adding additional vectors that are orthogonal to those columns. But necessarily by our derivation above, those have to be in the null space of either A transpose A or A transpose. Does that make sense? Then essentially what we can show is that now we're going to define a sigma which is no longer square. It's in in Rn, or M by N rather, with the property that sigma ij is equal to the square root of sigma I if I equals j, and both of these are less than or equal to k, right? And then 0 otherwise. Right? Then essentially, when the smoke clears, the expression that we're going to get is the following factorization. A, I'll write it big because it's important, is equal to U sigma V transpose. Do you see that? Because essentially now that I've completed these things and the columns of U and V are orthonormal, I can just invert them by multiplying by their transposes. Okay? And this is the SVD of our matrix, singular value decomposition. So here's a really cool thing. What did I need for the SVD to exist? Literally nothing. All matrices, every matrix out there in the universe has an SVD. This is different than the eigenvalue decomposition, where you need your matrix to be non-defective, right? Otherwise, like one thing you might remember from your linear algebra course is you end up doing all kinds of weird hacks, like this Jordan normal form, to account for matrices that are defective. But here, this is just a universal fact of linear algebra. Let's see if we can draw a picture. So, what are U and V? U and V are orthonormal matrices. So in particular, U transpose U is equal to I, right? Remember, A is M by M, so this, N. So this is like that. We have V transpose V is equal to the identity N by N, right? And sigma is a diagonal matrix of positive values, or at least non-negative values, right? By the way, we usually give these things a name. We call this little sigma I, which is a singular value. Okay? I'm glad we got this far, because this is what you need to finish your homework. Now you're good. But we can continue, because this is a fundamental object in numerical linear algebra. Okay? So in particular, Right, so I got so excited on the board, I forgot that we have slides. Right, so essentially we've shown all this. We have our decomposition, so on. Sorry. We completed our basis, and what we got was this thing. Ta-da! This is much better writing than what I had on the board. Okay, here's the thing. So remember that U and V here are orthogonal matrices. So like geometrically, we think of them as kind of like rotation and maybe a flip, right? So like, and what is sigma? This is a diagonal matrix of positive values. So the only thing it knows how to do is to take things and scale them along the coordinate axis, right? So now notice that this tells you something really geometric in nature about every matrix A, right? It says that every matrix, what does it do? It takes space, it rotates it, maybe inverts it, maybe it doesn't. Then it scales the coordinate axes, so it just stretches, and then it rotates again. That's it. Yeah. Here, I guess if sigma's non-square, then it's just saying maybe it slices off some coordinates. That's it. Isn't that cool? So that's what justifies that picture where you say that really when you take a circle and you're mapping it to an ellipse, right? Notice that like these two parts are just mapping the circle onto itself, and then this part is stretching the ellipse, but only like horizontally and vertically, right? So you kind of like put it into place, you horizontally, vertically stretch, and then you put it back, something like that. Everybody cool with that? Okay. Yeah, so that's really geometry. I should really revise this slide. It's not just rotate, it can also be rotated and invert, right? I can like multiply by -1. Okay, so to put a little bit of vocabulary here, in our SVD, we call the columns of U left singular vectors, and notice that those are a basis. Here I've written they span the row and the column space. This is true. Actually, the way we've defined it so far, they span all of Rn and Rm. But we'll see there's a special version of this that's a little more compact. And moreover, along the diagonal, you have non-negative values. Okay. All right. This suggests a numerical algorithm for computing SVD, right? Like, what do? Well, we take A, we calculate A transpose A, we do that product, and then we do QR iteration on that object. That's perfectly fine. That sounds fishy, right? Because we know that like computing A transpose A does like bad numerical stuff to a matrix, right? Like that's, remember like squares the condition number was sort of what we talked about for least squares. And had you looked at the eigenvalue conditioning thing you saw before, you'd see some similar conclusion. So that's not so good. So then there's sort of a contradiction, not a contradiction, but just like yet another one of these situations where the way that we derive a matrix factorization by hand is probably not the way that we do it on a computer, right? So again, so far we actually have an algorithm, right? Which is take A, take its outer product with itself, and just do eigenvectors, right? It turns out there's just many different paths to the SVD. Actually, in the second edition of the book, so I encourage you guys to read this part of the chapter carefully because it probably has typos in it. I go about proving a second one. I think we'll skip it in lecture because it's a little technical and not terribly geometric in nature. Which is, you might ask the question like, can I somehow get to the eigenvectors or to the singular values without having to compute that outer product, right? Without computing A transpose A? The answer is yes. So unfortunately for us, we still need to use the spectral theorem somewhere, right? Like notice that in order to justify this entire procedure that we just did, we needed to know that A transpose A was symmetric, right? That's what gave me the full set of eigenvectors. So the question is, how could I construct a symmetric matrix out of A? And A is not even square, right? Like, because that's like we only have one theorem, we might as well use it, right? So in particular, here's a little sneaky trick that you could have done just kind of experimentally, maybe. I could construct the following matrix where I put zeros down the diagonal. I put maybe A transpose here and A there. Right? So this is an M plus N by M plus N matrix. This thing's symmetric. So this thing has a full set of eigenvectors. And in fact, what you can show, which is really clean, is that essentially, when you compute eigenvectors of this augmented matrix, I think in the notes we call this B, that essentially they have a very nice form where like if you decompose them, they're just like, and you look at the components of these objects, you end up just getting the singular values back out, the singular vectors. Okay. So this is a different approach to SVD that's a little bit closer to the actual algorithms people do in practice, which is rather than taking A transpose A, you maybe compute this thing, which is 2 times as big, or sorry, like M plus N as big, and then do eigenvalues of this thing. Okay. So in any event, I think maybe we'll skip that in lecture here because we're moving a little slow. But if you look in the course notes, you'll see that that's how they get to the same thing, they being me. Okay, so one thing to note is that there are many different things that the universe calls SVD, and we should be a little bit careful to distinguish which one we're working with. So the thing that I've justified to you so far is something that often I think people call the full SVD, and it has to do with essentially the dimensions of U and V here. Okay. This is very similar to when we talked about like the compact QR decomposition. Okay. So in particular, in this particular version of the SVD, what's going to end up happening? So I have U sigma and V transpose. And remember, U and V are both square, right? So I've got like these big square matrices with a bunch of non-zeros in them. So there's the U. See, it's big because I made it big. And then I have sigma, which might not be square, and then like a square V transpose, like that. Okay? But like, let's say that this thing isn't square. So for example, this matrix is wider than it is tall, right? N is bigger than M. Then what's going to happen? Well, we know that sigma is a diagonal matrix. And then what's going to happen to the right of the diagonal? Like the diagonal stops before I get to the end of the matrix. This is all just a bunch of zeros, right? So notice that if I had taken V and decomposed it as V1, V2, like that, then in essence, the 0 is just zeroing out that V2 anyway, right? So in particular, this leads us to a different SVD, where I kind of remove this piece of the matrix, and correspondingly, I remove this part of V, right? Or by the way, if this were tall, then I'd have to do the same thing to U, right? And in that case, what would the dimensions be? They'd be, you know, like the min of M and N is going to show up in the dimensions of our matrices, right? And then there's a third version of the SVD, where let's say in addition to that, maybe I have some zeros here too while I'm at it. Right? Like maybe A transpose A is itself singular, then I can actually remove those ones as well and get an even smaller SVD. This is a little less common because, of course, the difference between null space and very close to null space is hard to distinguish. So this actually leads to 3 different SVDs. They have different names. These are names that I think are pretty common, but obviously read the documentation carefully. So I think all of us would agree that there's the full SVD where U and V contain an entire orthonormal basis. And then there's the sort of thin SVD where like it's we slice out the difference between M and N. And then there's like the sort of very compact SVD where we additionally kind of remove anything that's a 0 eigenvalue. Does that make sense? These are all valid factorizations of our matrix A. They just have different sizes. Notice in all of these cases, the columns of U and V are orthonormal. This is similar to some of the stuff you have to worry about on your homework, right? So in particular, if the columns are orthonormal, then you can always write that U transpose U is equal to identity, right? Because these are dot products between columns of matrices. But you cannot say that U transpose is identity unless it's square. Make sense? Any questions so far? Cool. So this is like the main matrix factorization out there in numerical linear algebra. It is so useful. Here are 2 different algorithms that we could use to compute SVD, both basically using our previous chapter of notes as sort of a subroutine. And there are many more. I mean, there exist some more specialized methods out there, of course, because again, with any of these small numerical linear algebra problems, so there's like somebody out there has built their whole career on studying it. But these are the sort of basic ones. Now here's the thing, like the SVD is like the big papa of matrix factorizations. Like basically any linear algebra problem out there in the universe almost that you want to solve, you can probably solve slightly easier with the SVD. Of course, what that should indicate to you is that like it's kind of expensive to compute this object, right? Like I probably don't want to do it for a big matrix. So for example, let's say I want to solve AX equals B. I have the full SVD of my matrix. AX equals B. Right? Then in particular, I have U sigma V transpose X equals B. Remember, like the inverse of U is just U transpose, right? So at the end of the day, X, assuming my matrix is invertible, what is it going to be? Well, it'll be V sigma inverse U transpose B. Yeah? And by the way, sigma inverse is really easy. It's just the diagonal matrix of 1 over the singular values, right? So what have we just proved? We just shown that like computing SVD is like at least as hard as Gaussian elimination, right? Which should give you some indication of its efficiency here. But yeah, so hopefully I did that right. Yeah. And in fact, we can do more than that. So in particular, can I do it in 5 minutes? I can do it in 5 minutes. So far in this course, we started by talking about invertible linear systems. Then we talked about least squares problems. There's a third thing, which is underdetermined, right? Where I want to solve ax equals b, but there's actually multiple x's that'll give me the same b. So here's a kind of fun thing that you can do, which we're going to do in 5 minutes or less, I promise. Is let's say I want to glue all of these problems together, right? So like, if my matrix is invertible, I want A inverse B. If it's not invertible and it's too big, I want the least square solution. And if it's too small, I'd like the solution with smallest norm. Okay? So remember that in general, if I want to solve this problem, for any A and B over or underdetermined, or perfectly determined, right? I think one thing we can all agree on, I hope, is that A transpose AX is equal to A transpose B. Okay? Notice that if there's multiple x's that give me B, then this objective function just has more than 1 zeros, and like such as life. But they will all satisfy this condition. Okay. So here's a really sneaky thing that we can do. Here's a weird optimization problem, which is the following. Minimize the norm of x subject to the constraint A transpose AX equals A transpose B. Why would I do that? Let's think about those 3 cases. So suppose that A is invertible. Well, then there's only one x that satisfies the constraint, which is A inverse B, right? Similarly, if A is overdetermined, then the only x that satisfies the constraint is the least square solution. And when the system is underdetermined, now it's going to give me the one with least norm among the solutions to this optimization problem. Yes, Axel. Well, what I'm saying is if the least squares problem only has one solution, then this thing clearly will give it to you. Yeah. Okay. So I think we can solve this really, really easily using the SVD. Okay. So in particular, let's say that I write A is equal to U sigma V transpose, like that, right? Then in particular, A transpose A is equal to V sigma transpose U sigma V transpose, okay? Which is equal to V sigma squared. I'm sorry, I should be careful not to square here because it might not be squared. I guess sigma transpose sigma V transpose. Okay. Have I made a mistake? No. Okay. So in particular, AX equals B can be mapped on to a different linear system, which is sigma transpose sigma Y equals sigma transpose D, where I choose Y to be equal to V transpose X. Right, so think about like putting an X here, right? Like that, I guess. So I'm going to factor this guy here, right? This is the identity. Or I guess this is probably a better place, right? And I'm going to pre-multiply both sides by V transpose U. And D we're going to define to be U transpose B. Okay. So after our change of variables, essentially now we have a new optimization problem, which is to minimize the norm of Y, subject to the constraint that sigma transpose sigma Y is equal to sigma transpose D. Okay. But this is kind of convenient, because notice that this problem decouples among the elements of Y, right? There's actually nothing here that makes any 2 elements of Y talk to each other. In particular, what is this constraint? Well, if we think about it, if we just look down the diagonal of this matrix, we're going to get the following expression, which is sigma I squared times yi is equal to sigma I d, right? You see that? Because like here's sigma squared, which comes from this guy, and then this is sigma I times d I. Okay. Remember, our input data is d, and our output is y, which is really x once after our transformation. Okay. So in particular, this gives us a form for y, because there's two cases, right? Either sigma is equal to 0 or it's not, right? So if sigma is not equal to 0, well, then I can divide both sides by sigma squared. And what I'm going to get is di over sigma if sigma I is non-zero. And otherwise, notice that essentially the constraint is 0 equals 0. I haven't constrained yi at all. And I want to minimize the norm of y. So the smallest thing that I can possibly do is to just put 0. Like that. Cool? In particular, what we have shown, oh no, is I thought I could use the last board here and still have space. And now I'm out of space, and this one doesn't move. Ah, all right. We have shown that y is equal to sigma plus times d, where sigma plus is equal to diagonal matrix of either 1 over sigma I if sigma I is non-zero and 0 otherwise. Like that. Right? So anytime that I have a sigma that it makes sense to compute the reciprocal, I do, and otherwise I put a 0 there. Okay? So unraveling our definition, we have that x is equal to vy, right? Which is going to be equal to v sigma plus u transpose b. Okay? Notice this is the same as the solution to the linear system we saw on the previous slide. It's just now there's a plus here instead of an inverse. Okay? If you don't believe me, because I see some squints here. Yeah, there it is. So notice that like, we have this expression here for solving ax equals b. And indeed, if sigma contains all non-zero values down its diagonal, which would correspond to the invertible case, then I recovered that thing. Right? And otherwise, I just zero out stuff when I compute the reciprocal. Okay? So in any event, this matrix has a special name. It is called the pseudo-inverse of my matrix A. Sorry, as usual, I anticipated. We call that A+. The idea is that when A is invertible, it's the inverse of A. And otherwise, it's this other thing, which is the inverse or the thing that gives me the least norm solution in all the parts where it's not invertible. Cool? All right, so now we've managed to couple together the underdetermined, overdetermined, and completely determined cases of linear systems. So with that, in the next lecture, we will continue to talk about applications of SVD. So we will do basically a version of your homework problem, fit rotation matrices to stuff, and talk about principal component analysis. All right, so have a lovely time. I'm happy to basically do Chris's office hours, but I'm going to do it in my office, so we got to go back to Stata Center.